If there was once absolutely nothing, no space, no time, not even darkness itself, then how did an entire universe just appear? Think about it. You, me, galaxies, black holes, reality itself. All of it somehow erupted out of a moment where nothing was supposed to exist. But here's the mind breaker. What if nothing is a lie? What if the emptiest emptiness is secretly the most powerful thing in existence? In today's journey, we'll discover nothing became everything. Here is something that will blow your mind. Right now, at this very moment, you are made of atoms that were forged in the nuclear furnaces of dying stars billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing, all of it was created in stellar explosions so violent they briefly outshone entire galaxies. But here is the real question. Why does any of it exist at all? This is not some abstract thought exercise. This is the single most important unsolved mystery in all of science. And the answer, when we finally find it, will change everything we think we know about reality. Let me tell you what we know for certain. 13.8 billion years ago, our universe exploded into existence. We call it the Big Bang, but that name is misleading. It was not an explosion in space. It was an explosion of space itself. Every point in the universe was the center of this explosion. Space, time, matter, energy, everything erupted from a state so small, so dense, so hot that our current physics cannot even describe it. Think about that for a second. Before the Big Bang, there was no before. Time itself did not exist. There was no space to expand into, no stage for the cosmic drama to unfold upon. The universe did not explode into an empty void. The universe created the void as it exploded, and we have proof. In 1964, two scientists named Arno Penzias and Robert Wilson were trying to eliminate annoying static from a radio antenna. No matter what they did, they could not get rid of this persistent hiss. It was coming from everywhere, all at once. What they had stumbled upon was the afterglow of creation itself, the cosmic microwave background radiation, the fossil light from when the universe was just 380,000 years old. This discovery won them the Nobel Prize. It proved beyond any doubt that the Big Bang actually happened. But here is where things get really weird. If the Big Bang created everything, what created the Big Bang? Where did all that energy come from? Where did the material, the stuff of existence, originate? For thousands of years, humans have operated under one fundamental assumption. Nothing comes from nothing. You cannot get something from absolutely nothing. It is common sense. It is logic. It is how the universe works. Right? Wrong. Modern physics is about to shatter that assumption, and when it does, reality will never look the same again. But before we get there, let me show you something even more disturbing, the future of our universe. Because understanding where we are going helps us understand where we came from. Physicist Brian Cox has calculated the ultimate fate of everything, and it is terrifying. Fast forward trillions of years into the future. Every star in every galaxy burns out. The universe keeps expanding. Galaxies drift apart so far that light from one can never reach another. The cosmos becomes a graveyard of dead stars, frozen planets, and eventually black holes. But even black holes do not last forever. Through a process called Hawking radiation, they slowly evaporate. It takes an incomprehensibly long time. A black hole with the mass of our sun would take 10 to the power of 67 years to disappear. Supermassive black holes take even longer, but eventually they all evaporate. Every single one. What is left? Nothing but photons, particles of light spreading through an ever-expanding universe. Space keeps stretching. These photons get pulled so far apart that they can never interact with anything ever again. The temperature of the universe approaches absolute zero. No stars, no light, no heat, no life, no motion, no events. Nothing happens. Nothing can happen. Time becomes meaningless because there is nothing to measure time with. This is called heat death, maximum entropy, the ultimate state of disorder. The universe reaches a condition where no energy is available to do any work. Everything just stops. It sounds like the end, the final curtain, game over. But what if it is not the end? What if it is the beginning? Here is where your brain needs to stretch. Some of the most brilliant physicists alive today are proposing something absolutely wild. What if that dead, cold, empty universe is exactly the condition needed to trigger the next Big Bang? What if universe death is actually universe rebirth? Think about the implications. If this is true, our Big Bang was not the first. It was just the latest in an infinite chain of cosmic cycles. Before our universe, there was another one, and before that, another, and another, stretching back forever, each one living, dying, and giving birth to the next. But wait, how can a dead universe create a new one? Where does the energy come from? This is where physics gets absolutely insane. Remember that assumption we talked about. Nothing comes from nothing. Quantum mechanics has discovered something shocking. Empty space is not actually empty. Even in a perfect vacuum with no particles, no matter, no radiation, nothing at all, the quantum fields are still there, and these fields are buzzing with activity. Virtual particles pop in and out of existence constantly. Matter and antimatter spontaneously appear, exist for a fraction of a second, and then annihilate each other. This is not speculation. We have measured this. We have built technologies that exploit this. The quantum vacuum is not nothing. It is a seething ocean of potential energy. So here is the mind-bending part. If empty space has energy, and our universe is heading toward a state of maximum emptiness, then that emptiness itself might contain enough energy to spark a new Big Bang. The death of one universe creates the conditions for the birth of the next. This changes everything. It means creation does not require a creator. It means the universe can be eternal without violating the laws of physics. It means our Big Bang was not the ultimate beginning. It was just a phase transition, like water freezing into ice or ice melting into water, one state of reality transforming into another. But how do we know this is true? How can we test it? Can we find evidence that our universe came from a previous one? Can we detect fingerprints of a reality that existed before time itself began? Yes, we can, and we are looking for them right now. The cosmic microwave background radiation, that baby photo of our universe, might contain hidden messages, patterns and anomalies that do not fit standard Big Bang theory. Some physicists believe these are echoes from a previous cosmic cycle, ghosts of ancient black holes that evaporated just before our Big Bang ignited. If we can decode these signals, we will have proof that our universe is just one chapter in an eternal story. And here is the kicker. If the universe cycles forever, that means everything that has ever happened will happen again. Not exactly the same, because quantum randomness ensures variation, but similar, infinite versions of reality playing out across infinite cosmic cycles. Somewhere in the deep future, after our universe dies and is reborn countless times, There might be another version of you reading these exact words, or maybe not these exact words, but something close. The possibilities are literally endless. This is not science fiction. This is cutting-edge cosmology, and it is forcing us to completely rethink the nature of existence itself. In part 1, we asked a brutal question. If our universe can be born from an almost nothing, then what exactly is that almost nothing made of? If the death of a previous universe can somehow light the fuse for a new Big Bang, then what happens next? How does that initial inferno turn into real stuff, into the matter that makes stars, planets, and eventually you? If you imagine the Big Bang as a blinding flash and then instantly galaxies and atoms appear, then your mental picture is wrong. The early universe was not a fireworks show. It was a slow, brutal, physics-driven evolution. And if you understand that evolution, then you start to see how fragile and improbable your own existence really is. Let us roll the clock back to the first moments after the Big Bang. Not years, not days, not even seconds. We are talking about millionths of a second, then billionths, then even less. At the very beginning, the universe is unimaginably hot and dense. Temperatures are so extreme that matter as you know it cannot exist. No atoms, no nuclei, not even protons or neutrons, just a seething soup of fundamental ingredients, quarks, gluons, photons, and pure energy. If you drop a human being into that environment, every molecule in their body would be ripped apart instantly. If you drop an atom, it would not survive either. The laws of physics at that scale are ruthless. Only the most basic building blocks can exist, and even they are locked in a violent dance. Now let us move forward to a critical moment, about 10,000th of a second after the Big Bang. That is 0.0001 seconds. This is when something historic happens. The universe cools just enough for quarks to start binding together. And when that happens, the first familiar particles appear. Protons and neutrons, the building blocks of atomic nuclei. If the universe had cooled too fast, then these particles could have clumped in a chaotic way and destroyed the precise balance that nuclear physics needs. If it had cooled too slowly, then high-energy collisions would keep smashing everything apart before it could stabilize. But the cooling rate was just right. If you ask why is that cooling rate so precise, then you are already touching one of the deepest fine-tuning puzzles in cosmology. Now, we have protons and neutrons. That sounds like a big win. But the universe faces another deadly problem: antimatter. For every particle of matter, there exists a twin with opposite charge called antimatter. If a proton meets an antiproton, they annihilate in a flash of pure energy. In the early universe, matter and antimatter were being created in almost equal amounts. Almost equal. That almost is the reason you are here. If the universe had produced exactly equal amounts of matter and antimatter, then everything would have annihilated. No leftover particles, no atoms, no stars, just a universe full of radiation and nothing else. Game over. No galaxies, no life, no you. But for some reason, and this is still one of the great unsolved mysteries in physics, there was a tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. The universe allowed a 1 in a billion asymmetry. That does not sound like much, but when the annihilation chaos ended, that tiny excess of matter, that 1 in a billion, became everything. Every star, every planet, every molecule in your body is built from that leftover matter. If that asymmetry had been slightly different, then the universe would be radically changed. If there had been less matter, then maybe no large-scale structures would form. If there had been more, then the entire evolution of stars and galaxies would be altered. So now we have a universe filled with protons, neutrons, electrons, radiation, and an insane amount of heat. But we still do not have atoms. The problem is that the universe is still too hot for electrons to settle into stable orbits around nuclei. Any time an electron tries to bind, a high-energy photon slams into it and rips it away. Matter wants to form, but the radiation bath is too violent. If you imagine trying to build a sandcastle in the middle of a hurricane, then you get the idea. The structure keeps trying to appear, but the environment keeps destroying it. For the first few 100,000 years, the universe is a plasma, a glowing, opaque fluid of charged particles and light. Photons cannot travel far without smashing into electrons. It is like trying to see through the inside of a star, bright, hot, and completely foggy. So when do atoms finally win? Roughly 380,000 years after the Big Bang, the universe has expanded and cooled enough that electrons can finally bind to nuclei without being instantly knocked free. This epoch is called recombination. For the first time, neutral atoms form, mostly hydrogen, with a bit of helium and traces of lithium. If that sounds simple, then remember this. That moment is the first time the universe becomes transparent. Photons can fly freely across space without constantly colliding. The cosmic microwave background that we observe today is literally the light released when the universe stopped being a plasma and became a gas of neutral atoms. If those conditions had not been reached, then we would not have that fossil light. And without that light, we would not have one of the most important tools in cosmology. But let us go even deeper. Earlier, I told you that empty space is not truly empty. Quantum fields fill every point of space. Even a vacuum is buzzing with energy. This is not philosophy. This is tested physics. We see the effects of quantum fluctuations in precise experiments, such as the Casimir effect and the behavior of subatomic particles in accelerators. In this picture, particles are not tiny billiard balls flying through space. They are local excitations of fields. When the field jumps in a certain way, a particle appears. When it relaxes, the particle disappears. That is why in a vacuum, pairs of virtual particles constantly pop into and out of existence. They are brief ripples in the underlying fields. So when we say that after the Big Bang the universe was full of energy and fields, what we really mean is that space itself was an active, vibrating stage. Matter emerges from patterns in those fields. If the fields did not have the right structure, then stable particles would not exist. If the quantum rules were slightly different, then maybe no protons would form, no chemistry, no complexity. This is where the phrase "even empty space is buzzing with ghost particles" becomes more than a metaphor. It is a literal statement about the quantum nature of reality. Every cubic centimeter of what you think of as nothing is actually an arena of constant activity, and that vacuum energy may have played a crucial role in the expansion of the early universe and in the formation of the first matter. But here is the twist. Even this quantum vacuum is still something. It has properties. It obeys laws. It has energy. Philosophers will remind you that we have not yet reached true nothing. We have not explained how the laws themselves arise. Physics can show you how matter springs out of fields, but it still assumes the existence of the fields and the rules they follow. If you ask where did those rules come from, then you are stepping into the next layer of the mystery. So by the time our universe is a few 100,000 years old, we have a transparent cosmos filled with hydrogen and helium atoms, bathed in a fading glow of primordial light. No stars yet, no galaxies, just a nearly uniform gas stretched across space. But hidden in that gas are tiny irregularities, slight over-densities and under-densities, seeded by quantum fluctuations from the earliest moments. If gravity acts on those tiny differences, then what happens? If slightly denser regions pull a bit more strongly, then they attract more matter, grow even denser, and eventually collapse into the first stars and galaxies. That is how structure begins. That is how the universe transforms from a smooth fog into a cosmic web. And that is where our story is heading next. In part 3, we are not just going to talk about atoms and stars. We are going to rewind even further to a time before protons, before quarks, before even space and time behaved like anything you would recognize. We are going straight into the Planck epoch, where the known laws of physics fall apart and reality turns into something far stranger. If you think what you have heard so far is mind-bending, then you are not ready for what happens when space-time itself becomes unstable. We left off at a universe filled with atoms, transparent for the first time, ready to form stars and galaxies. But if you think we have reached the bottom of this cosmic rabbit hole, then you are in for a shock, because now we are going to rewind past everything I just told you, past the formation of atoms, past the birth of protons and neutrons, past even the moment when quarks first appeared. We are going back to a time so early, so extreme, that the very concepts of space and time stop making sense. Welcome to the Planck epoch, the first 10 to the power of negative 43 seconds after the Big Bang. That number is so small it is almost meaningless to human intuition. If you took 1 second and divided it into 10 trillion pieces, you would be in the ballpark. This is not just early. This is the earliest moment physics can even attempt to discuss. And here is the brutal truth. At this scale, everything we know about reality breaks down. Our two most successful theories, general relativity and quantum mechanics, they both fail. If you try to use Einstein's equations to describe spacetime at the Planck scale, then you get infinities and nonsensical answers. If you try to use quantum mechanics to describe gravity, then the math explodes. The theories cannot talk to each other. They are like two different languages describing the same scene, but neither one making complete sense. So what does that mean? It means we do not have a working theory of quantum gravity. We do not know how to describe what spacetime actually is when it is compressed to sizes smaller than the Planck length, which is about 10 to the power of negative 35 meters. That is 20 orders of magnitude smaller than a proton. At that scale, space and time themselves become unstable. They stop being the smooth fabric you imagine and turn into something chaotic, something foamy, something we can barely conceptualize. If you could somehow zoom in to look at space-time at the Planck scale, then what would you see? Not empty smooth geometry. You would see a churning sea of quantum fluctuations, tiny wormholes opening and closing, virtual black holes popping in and out of existence. Space and time tangled together in knots. This is what physicists call quantum foam or space-time foam. Reality at its most fundamental level is not calm. It is a violent, seething cauldron of uncertainty. Now think about what this means for the Big Bang. If we roll the clock all the way back to the Planck epoch, then the entire observable universe, everything we can see today, was compressed into a region smaller than an atom. But it was not just matter that was compressed. Space itself was that small. Time itself was barely ticking. The rules of cause and effect, the idea that one event leads to another in sequence, those concepts might not even apply. If time is quantized, if it comes in discrete chunks at the Planck scale, then asking what happened before that first tick is like asking what is north of the North Pole. The question itself stops making sense, but physicists do not give up that easily. If our current theories cannot describe the Planck epoch, then we need new theories, and that is where things get wildly speculative, but also incredibly exciting. One major candidate is string theory. Instead of treating particles as point-like objects, string theory says they are tiny vibrating loops of energy. Different vibrations produce different particles. An electron is one vibration pattern, a photon is another, and crucially, one of those vibration patterns corresponds to the graviton, the hypothetical particle that carries gravity. If string theory is correct, then it naturally unifies quantum mechanics and gravity into one framework. But string theory comes with baggage. It requires extra dimensions, not just the 3 dimensions of space and one of time that we experience, but potentially 10 or 11 total dimensions. If that sounds insane, then consider this. Those extra dimensions could be curled up so small that we never notice them in everyday life. Imagine an ant walking on a garden hose. From far away, the hose looks one-dimensional, just a line. But if you zoom in close enough, then you see the ant can also move around the circumference. That second dimension was always there, just hidden by scale. String theory says reality works the same way. Extra dimensions exist, but are compactified at sizes near the Planck length. Another approach is loop quantum gravity. This theory takes a completely different route. Instead of starting with particles and fields, it starts with space-time itself. It says that space is not continuous, but is made of discrete loops, like a fabric woven from quantum threads. If you zoom in far enough, then you do not see smooth space. You see a network of interconnected loops. Time is also quantized. It ticks forward in tiny jumps. In this picture, the Big Bang is not a singularity where everything breaks. It is a quantum bounce. The universe contracts to a minimum size, then rebounds outward. Our Big Bang could be the rebound from a previous collapsing universe. Both of these theories, string theory and loop quantum gravity, are attempts to answer the same question. What is space-time really made of? If you can answer that, then you can describe what happened at the Planck epoch. You can peer into the first moment of creation and understand the quantum state that gave birth to everything. But here is the problem. We have no experimental evidence yet to confirm either theory. We cannot build particle accelerators powerful enough to test physics at the Planck scale. The energies required are trillions of times higher than anything we can produce. So right now, these ideas remain mathematical frameworks. Beautiful, elegant, and possibly correct, but unproven. Still, they teach us something profound. They tell us that space and time are not fundamental. They emerge from something deeper. Just like temperature emerges from the motion of molecules, space-time might emerge from more basic quantum structures. If that is true, then asking what existed before the Big Bang is the wrong question. Time itself is a product of the universe. There is no before if time started with the Big Bang. But wait, if space and time emerge, then what are they emerging from? What is the substrate? What is the deeper reality beneath space-time? Some physicists think it is pure information. Others think it is quantum entanglement connecting distant parts of space. Still others believe it is something we have not even imagined yet, a concept so alien that our current vocabulary cannot describe it. Let me give you an analogy. Imagine you are playing a video game. Inside the game, objects have positions, they move through space, events happen in sequence. But if you step outside the game and look at the computer running it, then you see none of that. You see circuits, processors, electrical signals. The space and time inside the game are not fundamental. They are generated by the hardware. Maybe our universe works the same way. Maybe space-time is the user interface, and the real physics happens at a level we cannot directly perceive. This is not mysticism. This is serious theoretical physics exploring the foundations of reality. And if any of these ideas are correct, then the implications are staggering. It means the universe at its core is not made of stuff. It is made of relationships, correlations, patterns of information encoded in quantum states. Now let us bring this back to the Big Bang. At the Planck epoch, space and time are undefined. The universe is a quantum blur. Then something happens. The temperature drops just slightly. The quantum foam stabilizes. Space and time crystallize out of the chaos, like ice forming from water. And once that happens, the clock starts. Cause and effect begin. The universe becomes something we can describe with equations. But what triggered that transition? What made the quantum foam settle into classical space-time? This is where we need to understand the initial quantum state of the universe. And that is one of the most speculative, most debated questions in all of cosmology. If the universe started in a specific quantum state, then the laws of quantum mechanics would dictate how it evolved. The initial conditions would determine everything that came after. The formation of particles, the slight asymmetry between matter and antimatter, the tiny density fluctuations that seeded galaxies, all of it could trace back to that first quantum state. But here is the mystery. Where did that quantum state come from? Was it random? Was it inevitable? Was it chosen by some deeper principle we have not discovered yet? Or is the question itself meaningless, because quantum states do not have causes in the usual sense? This is where physics reaches its current edge. We can describe the universe from a tiny fraction of a second after the Big Bang all the way to today with incredible precision. But that first fraction of a second, that Planck epoch, remains a locked door, and behind that door might be the answer to why anything exists at all. In Part 4, we are going to tackle that question head-on. We are going to explore the wildest, most ambitious theories about the origin of the universe. From cyclic models where universes are born from the ashes of previous ones, to multiverse scenarios where our Big Bang is just one bubble in an infinite sea. If you thought space-time foam was strange, then buckle up, because we are about to enter territory where science and philosophy collide in the most spectacular way possible. By now, you can see how deep this rabbit hole goes. In Part 2, we watched the first matter crystallize out of a furious quantum plasma. In Part 3, we went even deeper and saw space-time itself dissolving into quantum foam at the Planck epoch. We reach the edge where our best theories fail, and where space and time stop behaving like anything familiar. So now the question becomes unavoidable. If space-time and matter are not fundamental, if they emerge from some deeper quantum reality, then what started that deeper reality? What is the origin of the first quantum state of the universe? If you want a truly mind-bending question, then ask this. If there was a first quantum state, then why that state and not another? If the universe could have begun in a different configuration, then what selected this specific one that leads to stars, galaxies, and eventually brains able to ask these questions? And if nothing physical existed before that state, then what does it even mean to say it was caused? This is the frontier where physics becomes extremely speculative. We can no longer run controlled experiments about the birth of everything, so we have to rely on mathematical consistency, indirect evidence, and logical coherence. Some people bring in God or a cosmic designer at this point. That is one kind of answer, but as scientists we also want to know if the universe can explain itself. If the laws of physics are complete, then can they give us a universe from almost nothing without needing an external trigger? Let us start with one idea that sounds simple but is incredibly powerful: the concept of a quantum universe. In quantum mechanics, if you have a system, then you do not describe it with definite positions and velocities. You describe it with a wave function, a mathematical object that encodes all possible configurations of that system and their probabilities. Now imagine applying that logic not to an electron or an atom, but to the entire universe. Then the whole cosmos is described by a single wave function. The universe is not just in one state, it is a superposition of many possible histories. If that is true, then the origin question changes. We no longer ask what caused the universe in a classical sense. Instead, we ask what is the initial form of the wave function of the universe. Stephen Hawking and James Hartle proposed something radical called the no-boundary proposal. Roughly speaking, they suggested that if you go back to the very beginning, then time behaves like a spatial dimension. The universe is finite but without a boundary, like the surface of a sphere. There is no sharp edge, no starting instant, where the usual notion of time begins. In that sense, the universe simply is. If there is no boundary in the past, then there is no need for a cause in the traditional sense. But that is only one approach. Another family of ideas tries to keep things more concrete by imagining that our Big Bang is not unique. Instead, it is one event in a larger eternal framework. If you accept that, then you get multiverse and cyclic cosmology models. Imagine a vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants. In some regions, space is inflating, stretching faster than light speed. In others, the inflation slows down, energy condenses, and a Big Bang-like event occurs, birthing a bubble universe. Our observable universe would then be one bubble in a much larger multiverse. If inflation is eternal into the future and into the past, then Big Bangs happen over and over, not in time inside one universe, but as separate regions of a larger space-time. If that is true, then the question why this universe becomes why this region in the multiverse. But there is another, more geometrically elegant, and in some ways more disturbing idea. The universe as a cyclic phoenix, reborn from its own ashes. And at the center of this idea stands Roger Penrose and his conformal cyclic cosmology. Penrose asks a very strange question. What does it mean for the universe to be infinitely large and infinitely old? And what does it mean for it to be infinitely small and infinitely hot? If you have a universe that expands forever, cools down and thins out until there are only massless particles like photons left, then size and time start to lose physical meaning. If everything is massless, then there is no preferred length scale, no clock that can distinguish one moment from another. In that ultra-cold, ultra-empty end state, the universe has no meaningful notion of distance or duration. Penrose calls that a conformal universe. Only the shapes of things matter, not their scale. Now here comes the twist. The very early universe, just after the Big Bang, is also special. It is incredibly hot and dense, but again, scale is weird. When energies are that high, masses become negligible, and the physics starts to look similar to the ultra-cold end state. If both extreme futures and extreme beginnings lose any absolute sense of scale, then Penrose says you can mathematically glue them together. You can take the dead universe at the end of one cosmic era, rescale it using conformal geometry, and reinterpret it as the hot Big Bang of the next era. In other words, what looks like the heat death of one universe, filled with stretched-out low-energy photons and evaporated black hole remnants, can be mapped geometrically onto the initial conditions of a new universe. The old age infinity of one cosmos becomes the young age zero of the next. Penrose calls each complete cycle an aeon. If you follow that idea, then our Big Bang was not the birth of everything from absolute nothing. It was a transition, a rebirth from an ultra-diluted, almost featureless state left over from a previous aeon. Almost nothing, but not quite. An incredibly thin sea of radiation and subtle imprints from the black holes of the previous universe. Now, if you ask, how exactly could dead black holes help seed a new universe? Then Penrose has an answer. In his picture, black holes in one aeon eventually evaporate completely through Hawking radiation. The final release of their energy gets spread out across that ever-expanding, thinning universe. When you perform the conformal rescaling to match that end state to a new beginning, those last signals become part of the initial conditions of the next Big Bang. If that is right, then the new universe literally carries ghost fingerprints of the old one. The death cry of ancient black holes might echo across eons as subtle patterns buried in the cosmic microwave background. If this sounds like mystical reincarnation, then remember, this is a rigorous mathematical proposal built on conformal geometry and general relativity. There is no supernatural element needed. The entire universe becomes a self-recycling system. If there is no absolute beginning and no final end, then the age-old question what caused the universe gets replaced with a cycle. Each aeon is born from the last, in an eternal chain. But this raises a new question. If the universe can keep recycling itself, then what sets the rules of the game? The geometry, the quantum fields, the laws of physics that remain consistent from one aeon to the next. Where do they come from? Even in Penrose conformal cyclic cosmology, the deeper framework must exist. That framework is the almost nothing. It is not empty space in the simple sense. It is a mathematical and physical structure that allows aeons to exist at all. Here is where physics and philosophy start to blur. When we say almost nothing, we mean a state with as little structure as possible, but still obeying laws. Pure vacuum with quantum fields, a conformal geometry with no scale. Maybe a minimalist equation that generates universes the way a simple rule can generate an infinitely complex fractal. If such a rule exists, then perhaps the mystery is not why there is something rather than nothing, but why the simplest possible something automatically creates complexity. If the most basic mathematical structures tend to produce universes when allowed to play out, then perhaps existence is not a rare accident. Perhaps it is inevitable. If a lawful framework can exist at all, then maybe universes are the natural output. The challenge now is evidence. It is not enough for a theory to sound elegant or mind-blowing. It has to make predictions we can test, Conformal cyclic cosmology claims that signatures of previous aeons should be imprinted in our cosmic microwave background as subtle circular patterns, scars left by ancient black hole encounters. If those patterns are real and not statistical noise, then we might be staring at the first direct hints that our universe is not the first act, but the latest in a chain of cosmic cycles. In the next part, we will look at this evidence hunt in detail. We will see who claims to have found these ghostly circles, who disagrees, and what it would mean if they were confirmed. Because if we can prove that there was a universe before ours, then the question of origin shifts dramatically. The Big Bang stops being an ultimate beginning and becomes one chapter in a story that may have no first page. We just explored one of the boldest ideas in modern cosmology. Roger Penrose' conformal cyclic cosmology suggests that our universe was not born from absolute nothingness, but from the cold, dead remnants of a previous cosmic cycle. If that sounds too wild to be true, then you are thinking like a good scientist. Because the real question is not whether an idea sounds cool. The real question is whether we can test it. Can we actually find evidence that there was a universe before ours? And if so, where would we look? The answer lies in the oldest light we can see, the cosmic microwave background radiation. We talked about this before. It is the fossil glow left over from when the universe became transparent, about 380,000 years after the Big Bang. That light has been traveling through space ever since, cooling and stretching as the universe expands. Today, it fills the entire sky as a faint microwave hiss. If you tune an old analog television to static, then a tiny fraction of that static is actually the cosmic microwave background. You are seeing the afterglow of creation with your own eyes. Now here is why this light is so important. It is not perfectly uniform. There are tiny temperature fluctuations, hot spots and cold spots, at the level of about 1 part in 100,000. Those fluctuations are not random noise. They encode the seeds of all cosmic structure. The slightly denser regions in that primordial gas eventually collapsed under gravity to form galaxies and stars. If you map those fluctuations across the sky, then you are essentially reading the blueprint of the universe. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory have measured this pattern in exquisite detail. The data fits standard Big Bang cosmology incredibly well. The sizes, shapes, and statistical properties of those fluctuations match predictions from inflation theory and quantum mechanics. It is one of the greatest triumphs of modern physics. But if you look closely enough, then there are anomalies, tiny features that do not quite fit the simplest models. And that is where things get interesting. Penrose claims that if his conformal cyclic cosmology is correct, then we should see specific patterns imprinted in the cosmic microwave background. Not just random fluctuations, but organized structures left behind by catastrophic events from the previous aeon. Specifically, he predicts we should find concentric circles, rings of slightly different temperature centered on certain points in the sky. Why circles? Imagine 2 supermassive black holes colliding in the previous universe, just before it transitions into our Big Bang. That collision would release a massive burst of gravitational waves. Those waves ripple outward at the speed of light. Now remember, in conformal cyclic cosmology, the end of one aeon is mathematically mapped onto the beginning of the next. So if a gravitational wave was spreading through the dying universe, then when you rescale the geometry and flip into the new aeon, that wave gets imprinted as a circular pattern. The center of the circle marks where the black hole collision occurred in the previous universe. The ring itself is the frozen wavefront. If you detect multiple such circles, then you would have a smoking gun. Direct evidence that our cosmic microwave background carries echoes of events that happened before the Big Bang. Not philosophical speculation, not mathematical elegance, actual observational data proving that our universe inherited structure from something that came before. In 2010, Penrose and a colleague named Vahe Gurzadyan published a paper claiming they had found these circles. They analyzed the Wilkinson microwave anisotropy probe data and reported detecting low-variance concentric rings. In other words, circular regions where the temperature fluctuations were more uniform than random chance would predict. They argued this was exactly what conformal cyclic cosmology predicts. If true, it would be one of the most revolutionary discoveries in the history of science. The reaction was immediate and intense. Some researchers were intrigued, others were skeptical. Multiple teams reanalyzed the data using different statistical methods. Some claimed to reproduce the findings. Others said the circles were just random patterns that human brains are naturally good at picking out. Our minds evolve to recognize faces and shapes, so we sometimes see structure where there is none. This is a real problem in data analysis, especially when you are looking at noisy, complex maps. By 2011, several groups published counter-studies arguing that the circles Penrose found were consistent with statistical noise. If you randomly generate maps with similar properties to the real cosmic microwave background, then you can find circular patterns just by chance. The question became whether the circles in the real data were more significant than what you would expect from pure randomness, and the answer was not clear-cut. Some statistical tests said yes, others said no. Penrose pushed back. He argued that the critics were not using the right methods, that they were dismissing the signal too quickly. He and his collaborators refined their analysis and published follow-up papers claiming stronger evidence. They pointed to specific features in the Planck satellite data that seemed to match their predictions even better. But the broader cosmology community remained divided. So where does the evidence stand today? Honestly, it is inconclusive. There are hints, tantalizing patterns that might be echoes of a previous universe. But there is no consensus, no overwhelming proof that forces everyone to accept conformal cyclic cosmology. The signal, if it exists, is subtle. It sits right at the edge of what our current instruments can detect. We might need even more sensitive observations or entirely new ways of analyzing the data to settle the question. But let us think about what it would mean if Penrose is right. If we confirm that those circles are real, then we have proven that our Big Bang was not the beginning. The universe is far older than 13.8 billion years. It has lived through at least one complete cycle, possibly many. Time extends infinitely into the past, not as a linear timeline, but as a chain of aeons, each one inheriting faint memories from the last. And here is the kicker. If the universe cycles once, then why not infinitely? If one aeon can give birth to the next, then there is no reason for the process to stop. The universe becomes eternal in both directions. No absolute beginning, no final end. Just an endless sequence of deaths and rebirths, each one slightly different due to quantum randomness. If that is true, then every possible arrangement of matter and energy will eventually occur. Given infinite time and infinite cycles, anything that can happen will happen. There will be aeons where galaxies form differently, Aeons where stars burn out faster or slower. Aeons where intelligent life evolves on 1 billion worlds, or none at all. The universe explores every possible configuration, over and over, forever. Some versions of this idea connect to the many worlds interpretation of quantum mechanics. In that framework, every quantum event splits reality into multiple branches. Every time a particle could go left or right, both possibilities happen in separate branches of the wave function. If you combine that with cyclic cosmology, then you get a truly dizzying picture. Not just multiple aeons in sequence, but infinitely many parallel universes, each cycling through their own aeons, each exploring different quantum branches. Our Big Bang stops being special. It becomes just one bubble, in one aeon, in one branch of an infinite quantum multiverse. And yet, here we are. Conscious observers trying to piece together this cosmic puzzle from the inside. But there is another angle to this evidence hunt. Some researchers are not looking for circles in the cosmic microwave background. They are looking for other signatures, anomalies in the large-scale structure of galaxies, unusual patterns in gravitational wave data, unexpected features in the distribution of dark matter. If universes can collide or interact, if our bubble can bump into another bubble in the multiverse, then those events might leave scars we can detect. In 2015, a team claimed to find a cold spot in the cosmic microwave background that could be the result of a collision with another universe. The spot is unusually large and cold, harder to explain with standard inflation models. If it is a collision scar, then it would support the idea that our universe is not alone. But again, other explanations exist. It might just be a rare statistical fluctuation, or it might be caused by an enormous void in the distribution of galaxies along that line of sight. The pattern repeats, hints, possibilities, intriguing anomalies, but no definitive proof. Not yet. The universe is not giving up its secrets easily, and maybe that is appropriate. If the origin of everything is the deepest question we can ask, then it makes sense that the answer is not handed to us on a silver platter. We have to work for it. We have to build better instruments, refine our theories, challenge our assumptions, and keep searching. In the final part, we will tie all of this together. We will explore what it means if the universe truly is eternal, cycling through infinite deaths and rebirths. We will confront the philosophical implications of a cosmos that eats its own tail, and we will ask the ultimate question. If reality is an endless loop, then does existence need a cause at all? Or is the universe simply its own explanation, a self-contained system that requires nothing outside itself to justify why it is here? We have traveled a long way together, from the first moment after the Big Bang when protons and neutrons crystallized out of a quark soup, all the way back to the Planck epoch where space-time itself dissolves into quantum foam. We explored conformal cyclic cosmology, where the death of one universe becomes the birth of the next. We examined the evidence, the tantalizing hints in the cosmic microwave background that might be echoes from a previous aeon. Now we arrive at the final question. If the universe truly cycles forever, if it dies and is reborn in an endless loop, then what does that mean for existence itself? Let us start with the most radical version of this idea. Not just many cycles in sequence, but one eternal cycle that loops back on itself. Imagine time not as a line stretching infinitely forward and backward, but as a circle. The universe expands, cools, dies, and at the moment of ultimate heat death, it somehow connects back to its own Big Bang. The end and the beginning are the same event. Reality becomes an Ouroboros, the ancient symbol of a serpent eating its own tail. The universe does not need a first cause because there is no first moment. Every instant is both a consequence of what came before and a cause of what comes next. The loop is eternal and self-sufficient. If you think that sounds impossible, then consider this. In general relativity, time is not absolute. It is part of the fabric of space-time, and that fabric can bend, stretch, and even loop back on itself under the right conditions. Closed, time-like curves, solutions to Einstein equations where you could theoretically travel into your own past, have been studied for decades. Most physicists think they are not physically realizable because they lead to paradoxes, but mathematically, they exist. If space-time can curve in such extreme ways on small scales, then why not on cosmic scales? In a closed time-loop universe, causality becomes circular. If you ask what caused the Big Bang, then the answer is the heat death at the end. If you ask what caused the heat death, then the answer is the evolution that started with the Big Bang. The chain of cause and effect wraps around and bites its own tail. There is no external trigger needed. The universe sustains itself. But here is where things get even stranger. If the universe loops, then does it loop exactly the same way every time, or does each cycle differ? If quantum mechanics is true, then exact repetition is impossible. Quantum events are fundamentally random. The precise positions of particles, the outcomes of particle interactions, the specific configurations of matter, all of these have probabilistic elements. Even if the overall structure of each cycle is similar, the details will vary. You might have a cycle where Earth forms around a different star, a cycle where dinosaurs never go extinct, a cycle where humans never evolve, a cycle where an entirely different form of intelligence emerges. If that is true, then the universe is not just one loop. It is an infinite family of loops, each one exploring a different branch of quantum possibility. And if you take that idea to its limit, you arrive at the many worlds interpretation. Every quantum choice, every particle that could go left or right, every photon that could be absorbed or reflected, spawns a new branch of reality. The wave function never collapses. All possibilities happen. They just happen in parallel universes. Now combine that with cyclic cosmology. If every quantum possibility creates a new branch and every branch cycles through its own sequence of aeons, then you get a multiverse so vast it defies comprehension. Not just multiple Big Bangs in sequence, not just multiple bubble universes inflating in a larger space, but an infinite tree of branching realities, each one cycling through birth, death, and rebirth, each one exploring every possible configuration of matter and energy. In this picture, our universe, the one you are experiencing right now, is just one leaf on an infinite cosmic tree. There are versions of this universe where you made different choices, versions where history unfolded differently, versions where the laws of physics are slightly different because the initial quantum state was slightly different, and all of those versions are equally real. They all exist. They are all happening simultaneously in the quantum multiverse. If you find that overwhelming, then you are not alone. Even physicists who work on these ideas struggle with the implications, because if every possibility is real, then what makes this moment, this version of you, special? The answer might be nothing. You are just one instance of consciousness experiencing one branch of the infinite tree. Other versions of you are experiencing other branches, and from their perspective, their branch is the real one. But let us bring this back to the origin question. If the universe is an eternal loop or an infinite tree of loops, then does it need an origin at all? If there is no first moment, no absolute beginning, then the question what caused the universe loses its meaning. The universe simply is. It has always existed and will always exist, not in the sense of linear time stretching infinitely forward and backward, but in the sense of a self-contained logical structure that requires nothing outside itself. This is where physics and philosophy converge. Philosophers have long debated whether anything can be self-explanatory. Can something exist without an external cause? Traditional logic says no. Everything needs a reason. But maybe that logic only applies within the universe, not to the universe as a whole. If the universe is all there is, if it includes not just space and matter, but also the laws of physics themselves, then asking what caused it is like asking what is outside of everything. The question assumes there is an outside, but there might not be. Penrose conformal cyclic cosmology offers one version of this self-sufficient universe. The geometry of space-time, the behavior of quantum fields, the evolution from hot to cold, all of it conspires to create a cycle. The end state of one aeon has exactly the right properties to serve as the beginning state of the next. No external input needed, no creator required. The universe generates itself through its own internal logic. But even this picture assumes something. It assumes the existence of space-time, quantum fields, and the mathematical laws that govern them. If you ask where those come from, then you are back to the same mystery. Why these laws and not others? Why any laws at all? Why is there a framework that allows universes to exist? Some physicists think the answer lies in mathematics itself. They propose that mathematical structures are not just descriptions of reality. They are reality. If a consistent mathematical structure can exist, then it does exist, as a universe. Our universe is one such structure. The laws of physics we observe are simply the internal rules of that mathematical object. If that is true, then the multiverse is the collection of all possible mathematical structures. Every logically consistent set of rules corresponds to a real universe. This idea, called the mathematical universe hypothesis, is deeply controversial. Critics argue it explains nothing. It just pushes the mystery back one level. Why does mathematics exist? Why should logical consistency imply physical existence? But supporters argue it is the ultimate Occam razor. If you accept that abstract mathematical objects exist in some sense, and our universe clearly follows mathematical laws, then why not identify the two? Why add an extra layer of physical stuff when the math alone might be enough? If that view is correct, then the origin question vanishes. Mathematics does not need a cause. It is not a physical thing that comes into being. It just is. The truths of mathematics are timeless and necessary. 2 + 2 = 4 in all possible universes, including ones that never physically exist. If our universe is a mathematical structure, then it inherits that timeless necessity. It exists because it is logically possible, and everything that is logically possible exists as some form of reality. But whether you accept that or not, the cyclic model gives us something profound. It shows that the universe can be eternal without violating physics. It shows that the Big Bang does not have to be the ultimate beginning. It shows that nothingness might not be the default state. Maybe existence is more stable than non-existence. Maybe a universe that recycles itself is more natural than a universe that appears from true nothingness and then vanishes forever. And here is the strangest part. If the universe is a loop, then you are part of that loop. The atoms in your body have cycled through stars, through planets, through living organisms, and if conformal cyclic cosmology is right, through entire aeons. You are made of recycled stardust from recycled universes. Your existence is woven into the eternal tapestry of cosmic death and rebirth. In ancient mythology, the Ouroboros represented infinity, the eternal return, the cycle of destruction and creation. The Greeks used it, the Egyptians used it, Norse mythology had it. Now modern physics is discovering that this ancient symbol might be more than metaphor. It might be a literal description of reality. So we return to where we started. Why does anything exist? After 6 parts, after journeying through quantum fields and space-time foam and conformal geometry and cosmic microwave background anomalies, what is the answer? Maybe the answer is that existence does not need a reason outside itself. Maybe the universe is its own explanation, a self-sustaining loop of energy, matter, space and time, cycling forever, exploring every possibility, creating complexity out of simplicity, and then dissolving back into simplicity only to rise again. Complete emptiness becomes ultimate potential. Death becomes birth. The end becomes the beginning, and reality keeps eating its own tail, forever. If that is true, then the deepest mystery is not why there is something rather than nothing. The deepest mystery is why we ever thought nothing was the default. Maybe existence is the default. Maybe the universe cannot not exist. And maybe we are just beginning to understand why.